Okay, so let's do another example of minimization. I've got a more complicated DFA this time. So what was the first step of our algorithms? Let's have a look. So the first thing we have to do is, if there's any unreachable states, we can turf them immediately. So if we have a look at this diagram, it looks like the only state with no arrows pointing into it is going to be R. So we can freely throw that one out. We don't need that. And what states will we expect to be equivalent? Well, it looks like S1 and S3 are required because they look like they're doing a job, right? S1 is checking the first one and S3 is checking the second one. But S4, S5, and S6, once you're in one of the accepting states, you're sort of trapped in this like infinite death spiral and you can't get back out again. So it looks like once you're into an accepting state, if you can never leave it, which means these three states are likely to all be equivalent, right? So let's check that by running the algorithm. So once again, we group all non-final states together. And we group all the final states together. Because by default, we assume all states are equivalent, but we know final and non-final states aren't equivalent, so we split them into like the most general possible grouping. Okay? So now we're going to pick a character to split on. I can sort of be a little judicious in my choice here. Well, S3 looks like it goes to a different group regardless of what character, so in this case it doesn't actually really matter, so I guess we'll pick 0. S0 under a 0 goes all the way over here to S5, which is a different group. Oh, here we go. If I had picked 1, S0 had gone to S1 and stayed in the same group. But because I picked 0, I get 2 splits. S0 goes to S5, so that means S0 goes in a separate group. S1 goes to S3, so that means it stays in the same group. And S3 goes to S5. We don't write it separately, because S0 and S3 could be equivalent because they both go to the same group. So you actually group the S0 and the S3 together. You wouldn't split them into singletons immediately, right? Because if S1 stays in its group, so let me just like color code this. S1 stays in its group. S3 and S0 go to the different group. Which means S0 and S3 could be equivalent for all we know. We don't have enough evidence to declare these things different. So we put the S1 by itself, but we keep S0 and S3 together for the moment. S4, S5, and S6 under a 0 all sort of go to each other, so we can't split that up. So let's just write that down. Because 4 goes to 6, and 6 goes to 5, and 5 goes to 4. So now let's try splitting under a 1 and see what happens. Can't split singletons. S0 under a 1 goes to S1. So S0 goes to the S1 group, which means S0 is different. Or maybe, we'll see. And S3 goes to S4. So because S0 goes to the S1 group and S3 goes to the final state group, they're different. So we can split them. And this group here doesn't split. Okay. So because we split, we have to run both characters before we can declare the algorithm terminated. If you run 0, well, I can't split singletons, so they stay the same. Blah, blah, blah. And we already know because these all states go to each other, there can't be any splits. And then you have to do it with 1 again, and you get the same result. Because I can't split singletons, and I know each of these states all go to each other. Under a 1, 4 goes to 5, 5 to 6, and 6 back to 4, so no splits. So it looks like S4, S5, and S6 are all equivalent. Because I got to the end of the algorithm, I tried splitting on a 0, I tried splitting on a 1, nothing worked. Looks like these guys really are the same thing. Okay, so now what? It means I can now redraw my state diagram, missing 2 of the states. I can pick any single state out of these 3 to keep and toss the other 2 because I only need 1 out of the 3. And your choice actually doesn't matter. You'll end up with the same DFA. In fact, let's do 2 cases where I delete S5 and where I delete S6, and we'll show we get the same thing. I beg your pardon. Where I keep S6 and where I keep S5, and we'll show we get the same thing. So let's try deleting S4 and S5. So I'm going to get a new state diagram here. So I just redraw everything that isn't getting deleted. And, alright, so what are we going to keep? We're going to keep only S6. And can't draw those arrows, can't draw those arrows. Alright, so there's no more arrows I can draw. So now I have to fill in the gaps. So S3 under a 0 goes to S5. I know S5 is equivalent to S6, so I can draw an arrow here for 0. S3 under a 1 goes to S4, and S4 is the same as S6, so I can send S3 directly to S6. Okay, what else do I got to fill in? We'll have to fill in the transitions for S6. So what you do is you draw the states that you're not supposed to delete. You draw all the arrows that don't get deleted, and the ones that do, you have to refill in the arrows by sort of seeing what states they go to and then picking an equivalent state. So you just keep adding arrows until this thing is a DFA. That is, each state has one and only one place to go for each character. So what gaps are left? I don't know where to go for S6. S6 under 0 goes to S5, and S5 is the same as S6, so I send a 0 from S6 to itself. S6 under a 1 goes to S4, and S4 is the same as S6, so that means S6 goes to itself. Okay, so that's good, that's good. S1 has got gaps. S1 under a 0 goes to S4, and S4 is the same as S6, so I can send S4 to S6 under a 0. And S0 is missing, right? S0 under a 0 goes to S5, and S5 is the same as S6, so we put another transition here for a 0. Okay? Now let's try deleting a different state. So now I'm going to keep S5 and delete S4 and S6, and we'll see if we get the same result, which we should. So I'll do that in a different color. Here we go. So once again, I draw as much stuff as I can. S1, S3, and we're going to keep, we'll keep S5, and we'll toss the other ones. Okay. S0 under a 1 goes to S1, S0 under a 0 goes to S5, S1 under a 1 goes to S3, S1 under a 0 goes to S4, but S4 no longer exists, so we'll come back to it. S3 under a 0 goes to S5, and S4 and S6 are gone, which means all these transitions are gone. And that looks like about as much as I can draw, because all the transitions from S5 go to either S4 or S6, and they're missing now. So that's as much as I can copy. Now I've got to fill in the rest by seeing what states are equivalent. Under 0s and 1s, S5 goes to either S4 or S6, and S4 and S6 and S5 are all equivalent. So that means S5 under a 0 or a 1 goes straight back to itself. Where did S3 go? S3 under a 1 went to S4, and S4 is the same as S5, so that means S3 goes to S5 under a 1, so we can just change this transition to say 0 or 1. What else is missing? The S1 transition. S1 under 0 goes to S4, and S4 and S5 are the same thing, so we can add a transition here for 0. And fancy that. Up to relabeling S6 to S5, these DFAs really are equivalent, right? They might have different labels, but the point is their behavior is the same, so these are really equivalent DFAs. So we can see that it doesn't really matter what state we delete. We're going to get the same answer. So as an exercise, try constructing the equivalent DFA by deleting both S5 and S6. So delete S5, S6, so leave only S4 out of those three, so we're going to be keeping this one, and then construct the DFA, and then check that the answer you get is the same as my previous two answers, okay? So I'll leave that as an exercise to you.